All right, here's my crash course on the 555 circuit that we're going to do in the lab. You can kind of see the circuit over here. So you've got an RC network here. This is just straight going to be charging and discharging through here. The thing that I want you to notice is at pin 2, so we're making an astable multivibrator. So we've hooked up pin 2 to pin 6, and the reset just goes to VCC. Pin 3 is our output, pin 1 goes to ground, pin 8 goes straight to VCC, and we have resistors between pin 8 and pin 7, and again between pin 7 and pin 6, and then we have this charging capacitor here. Pin 5 is a control voltage. We're not going to use it as part of this lab, but you would do it if you were using the 555 to do any kind of pulse width modulation or trying to mess with the duty cycles and that kind of stuff. So basically I'm just going to go very briefly into what is in this circuit and what makes it work. So it really starts with a voltage divider, and because of that it doesn't particularly matter exactly which voltages you use. So we've just got a voltage divider here which divides the voltage equally in 3 ways. We've got 3 5K resistors here, which is one of the rumored ways the 555 got its name. Next we have a couple of comparators here. Or op amps that we're going to use as comparators. And this will come out here. So this comparator is going to be looking at 2/3 of VCC. This comparator is going to be looking at 1/3 of VCC. So if you look at these points here, this is ground, this is 1/3 of VCC, and this is 2/3 of VCC, and this of course is 3/3 or VCC. So what we're looking at here is this is basically pin 6, which is a threshold, and this is pin 2, which is the trigger. Now again, in our circuit we've connected pin 2 directly to pin 6, and we'll see why that makes a difference in a moment. So these outputs here just go to a SR latch, set, reset. You've got your Q and you've got your Q naught. So Q naught goes to pin 3, which is our output. The Q output goes to a transistor, which is basically just used as a switch. And this is pin 7, which is the discharge. So that's basically the internal circuitry of this in a simplified form, which explains how this is going to work and how we're going to get our astable multivibrator. So if we look at the output, so there's 2 things I want to look at the output, pin 2 and pin 6, which are connected together in this circuit, and pin 3. So if we have our output, which is pin 3, I'm using a 1 here, but this will be, let's say we're using 5 volts, this will be 5 volts. So when we start, basically the trigger is pin 2. So anytime pin 2 is less than 1/3 of VCC, that will reset the latch which makes Q 0 and makes the output 1. So if our trigger is less than 1/3 of VCC, then the output here will be high. And the other thing I want to look at is the output at pin 2 and pin 6. So what's going to happen when this is low? So we're going to be resetting the latch. So this will be 1. Sorry, when the latch is reset, this will be 0, this will be 1. So since the output here is pin 3, this is going to go up to plus 5 volts. Now, what's going to happen when this is 0 is this transistor is off. So when this transistor is on, it takes whatever's at pin 7 and just shorts it to ground. But since this transistor is off, this is open. So it's almost like this isn't here. And then basically what's going to happen is you're just going to have the voltage at this point, right? The voltage at this point is going to start at ground when it's first turned on, and it's going to start charging based on the value of the resistors and the capacitors. It's an RC network, so as soon as you get power, the voltage will start to increase. And it will increase. Now, when it gets to 2/3 of VCC, the threshold will be activated, because as soon as the voltage at pin 6 goes above 2/3 of VCC, then it sets the latch. So as soon as you get to 2/3 of VCC, which in this example, if we're using 5 volts, that would be 3 1/3 volts, so 3.33 volts. What's going to happen is, as soon as the threshold goes above 2/3 of VCC, this sets the latch, so now Q will be 1 and output is 0. So as soon as this reaches 2/3 of VCC, the output at pin 3 will go low. What also happens is this transistor is now on, which means whatever's at pin 7 goes straight to ground. So now this internally goes straight to ground, and now that will discharge, right? Because now basically you have a circuit where you have ground, resistor, capacitor with some voltage on it, and now this will discharge. So as it's discharging, the voltage will drop. But what's going to happen is, at some point, it's going to hit 1/3 VCC, and as soon as it gets to 1/3 of VCC, then you're going to activate the trigger again, because as soon as pin 2 and pin 6 are connected. So when this goes below 1/3 of VCC, it's going to reset the latch, making this 0 again, making this 1. So this turns off the transistor, which removes the short to ground from pin 7, which stops the discharging. And now it will start to charge again, because the output went high again. And then this will start to charge up again. And eventually it will reach this, that line should be straighter. Eventually it will reach 2/3 of VCC again, and then the pattern repeats. So once it reaches 2/3 of VCC, this is going to turn on this transistor, it's going to turn the output back to 0, and then it's going to start to discharge. And because pin 2 and pin 6 are connected together, what you're going to find is the voltage keeps bouncing back and forth between 2/3 of VCC and 1/3 of VCC. So the output at pin 3, if we're using 5 volts, will go from 0 to 5 volts, 5 volts back to 0, 0 to 5, 5 to 0. But if you look at the voltage right here, which is the voltage of pin 2 or pin 6, it will ping pong between 2/3 of VCC and 1/3 of VCC. So it will never go to 0 and will never go to 5. The reason it never goes to 5 is as soon as we hit 2/3 of VCC, it stops the charging. And as soon as we go to 1/3 of VCC, it starts the charging. So pin 2 and pin 6 will bounce back and forth. Now, when you build this in the lab, you will notice that the duty cycle of this circuit is much greater than 50%. Typically, when we do it in the lab, the duty cycle is around 64%, give or take. And the reason for that is all based on the RC network. So when the capacitor is charging, it's charging through C1, R2, and R1, right? And everything is based on R and C, which in this case, when you're charging, is C1, R2, and R1. However, when we're discharging, pin 7 is going straight to ground, so it's bypassing R1. So when we're charging, we're going through R1 plus R2 and C, of course, but when we're discharging, we're only going through R2. So that means in discharging there's less R, which means it's going to be faster. So when you're charging through R1 and R2. When you're discharging, you're only discharging through R2. So because there's less resistance, and the timing is based on the resistance and capacitance in the circuit, since you have less resistance on discharging, the discharge will be quicker, therefore the time that this spends low will be less than the time that it spends high. So the charging is longer than the discharging, which means the time high will be greater than the time low. Now, you can manipulate this a bit with the values of resistors that you choose, but unless you do certain modifications like diodes and changing certain things, if you just build this circuit as it is, you can play with the resistors a little bit, but typically your duty cycle will always be greater than 50%. And the reason the duty cycle will be greater than 50% is the charging time will always be greater than the discharging time, and the charging time is when the output is high. So since the charging time is more, the time high will be more, which means your duty cycle will be greater than 50%. So that's basically my crash course on the 555 and what's going on in your lab. When you display this in your lab, I always like to see the output on channel 1, and then I'd like to see the output at pin 2 or pin 6, so that you can see the charging and the discharging of the capacitor. Also, what I like to see is have both channels at the same volts per division and put the grounds together so you can overlay it. And when you overlay it, you'll see, if you put them at the grounds at the same place, you'll see that the charging and discharging goes between 1/3 and 2/3 of VCC. And that's because it's based on the voltage divider. The actual voltage you use doesn't matter. The proportions are what count here, so it should be the same even if you have a slightly different voltage. It will always go between 1/3 of VCC and 2/3 of VCC, whatever that is. And again, this is all based on the RC network, which is R1, R2, and C1. All right, so here we are at the oscilloscope, and I've put our 555 timer circuit on the scope. So what you're looking at on channel 1 here is the output, so that's going high and low here. And then what you're seeing on channel 2 is the charging and the discharging of the capacitor. So what I'm going to do is I'll put both of these at 1 volt per division, and then I'll put the grounds together. So you can see, so again, there's the output, the square wave that you get at pin 3, and this is at pin 2 and 6, and you can kind of see that it's going from 1/3 to 2/3 of VCC and staying and bouncing back and forth. So I'm just going to take channel 2 off for a second, and we'll take a look at the duty cycle. And the duty cycle on this particular one, these are different resistor values than we use in the lab, but you'll notice that even though the resistors are different, the duty cycle is still greater than 50%. It's showing, I think, 58.7% there. And we'll put channel 2 back on. So just again, this is the output. This is the output at pin 3. This is the charging and the discharging of the capacitor, and when I overlay the two of them by putting the grounds together, you can see that the charging and discharging is happening at the 1/3 and 2/3 of VCC points, and again that's because we have pins 2 and 6 tied together to create an astable multivibrator.